Welcome everyone to the ESG webinar, How Can Great Britain's Hydrogen Economy Develop Over the Next 30 Years? My name is Rupert Blackstone. I'm Chair of the Energy, Environment and Sustainability Group. And we are representing the IMechE, who are tackling the current practical engineering challenges of all the various strands of hydrogen as an energy sector. And the ESG perspective is focused on sustainability. And this is one of our series of webinars, which we'd actually established before the pandemic, and we found it a great way of reaching our wider audience. And it's good to have such great numbers attending today. Grant Wilson is a very valued member of ESG, and we've been using his slides on analysis of system-wide energy transmission and storage and consumption for some time, and I'm delighted to pass you on to him to start the webinar. And I'd ask you please to send your questions through as the webinar progresses, so that we don't have a gap between the end of the presentation and the questions at the end. So with this, I hope you enjoy the presentation, and we'll take questions afterwards. Thank you, and I'll pass you on to Grant. Thank you, Grant.
Good afternoon. I'm delighted to be giving this Institute of Mechanical Engineers webinar on how can Great Britain's hydrogen economy develop over the next 30 years. Since we first conceived of the webinar earlier in the year, there have been a number of wider reports and policy announcements, meaning the momentum and interest in hydrogen continues to grow. As a quick introduction, I am Dr. Grant Wilson. I lead the Energy Data Analytics Group in Chemical Engineering at the University of Birmingham. I've been investigating the scale and seasonality of energy supply and demand in the UK for many years. Although the UK has done well to lower the carbon intensity of electricity over the last decade, it needs to increase its focus into matching this with lower carbon forms of energy system flexibility. Currently, the flexibility of the wider energy system are underpinned by fossil fuels, primarily natural gas in the non-transport sectors. For this webinar, the climate and transport fuels data are at a UK level, whereas the electrical and gas data are at a level of Great Britain. If there is anything unclear in the webinar, please feel free to contact me using the email address. There is quite a bit to get through in 40 minutes, so the webinar is split into 3 parts. Part 1 is an overview on why hydrogen is likely to be a critical part of the energy system in 2050 at a global and a UK level. Part 2 is how could the UK develop its sustainable hydrogen economy over the next 30 years. And Part 3, delighted to answer any questions. It is important to state upfront and clearly that in the view of the Institute of Mechanical Engineers Energy, Environment and Sustainability Group, that in the long term, hydrogen must be produced in a sustainable manner. However, the group also recognises that in order to manage a smooth transition to a sustainable long-term future, certain existing unsustainable activities will need to remain in place in the short term. This is also part of the Institute of Mechanical Engineers' energy hierarchy. The use of natural gas and carbon dioxide capture, utilisation and storage, or CCUS, to create blue hydrogen is unsustainable, but it may fit within this near to medium term outlook as part of an overall longer term energy system transition. Turquoise hydrogen, produced through the pyrolysis of methane, is also unsustainable. It is felt by Germany in particular to offer an alternative fossil fuel based technology pathway other than the production of blue hydrogen using CCUS. However, the production of hydrogen from fossil fuels needs to be replaced as soon as is practical with hydrogen produced from sustainable sources. Ultimately, hydrogen has to be created from a range of non-fossil, low-carbon sources, such as primary electricity from renewable generation or from bio-based feedstocks. In terms of the cost differential between fossil-produced and sustainably produced hydrogen, governments will continue to have a range of options to encourage a shift from one to the other. Hydrogen is increasingly seen as a critical component of future energy systems. Indeed, in current energy systems, it is already a critical component as a part of fossil hydrocarbons. There's a growing body of evidence suggesting that sustainable hydrogen is likely to be a critical core component of net zero greenhouse gas economies, such as the recent reports and announcements from the European Commission stating that the end goal for the EU is clear: climate neutral energy system integration with renewable hydrogen and renewable electricity at its core. This announcement was preceded by Germany's national hydrogen strategy, which announced multi-billion euro support to develop a home market and international market for the development of hydrogen. In the UK, the importance of hydrogen to its net zero ambition is evidenced within the Committee on Climate Change's recent progress report to Parliament, where it is stated that low-carbon hydrogen is critical to achieving net zero and needs to be deployed at scale during the 2020s. Given the potential of the fuel across multiple sectors, a cross-cutting vision and strategy for a hydrogen economy will be required from government, with production and use starting from the early 2020s. Risk-sharing mechanisms for the first users and producers of low-carbon hydrogen are likely to be required in order to develop a market for low-carbon hydrogen. More detailed evidence on the roles for hydrogen is expected this December in the Committee on Climate Change's Carbon Budget 6 report, where a range of pathways to net zero greenhouse gases by 2050 will be presented. So what are the reasons underpinning the growing interest in hydrogen? Why is it being viewed as a critical component of net zero greenhouse gas economies? Firstly, it can help to decarbonise industrial feedstocks, such as for fertiliser and other products in the chemical sector. Secondly, it can provide high temperature process heat, can form the basis of synthetic liquid fuels, and act as a reducing agent for the production of steel. Thirdly, at a national level, it provides a potential method to store tens of terawatt hours of excess electrical generation from weather-dependent sources, potentially over seasonal timeframes. And fourthly, at a global level, it provides a potential method to ship tens of thousands of terawatt hours of energy between countries. In essence, hydrogen can help to decarbonise areas of economic activity that have limited other options to do so. Areas of interest for hydrogen or synthetic fuels using hydrogen in the UK also include forms of transport that are less suited to battery electrification. These include heavy goods vehicles, trains, shipping and aircraft. However, there is great competitive pressure from battery electric vehicles for other areas of transport. Also, given the UK's extensive natural gas network, there is considerable interest in whether these can be repurposed to distribute hydrogen for the provision of space heating and hot water. Again, there is significant competitive pressure from heat pumps of all types, including hybrid heat pumps. There is a lively ongoing discussion surrounding the repurposing of natural gas grids to carry hydrogen and the benefits and costs of doing so versus the cost of alternate means of delivering space heating and hot water to homes and businesses. Given the overview of why hydrogen is likely to be a critical component of future energy systems, the next slides will detail the energy vectors in Great Britain to get a better sense of the scale and seasonality of its existing energy system. Here we see the daily demand for electricity displayed as the red line over the years 2017 to August 2020. For a northern European country, the electrical demand is lower in the summer than it is in the winter. The green line shows the daily total supply of electricity from low carbon sources, including nuclear, wind, solar, biomass, and hydro. The y-axis is in units of gigawatt hours of demand or supply per day. We can see the winter peak daily electrical demand is just over 1 terawatt hour per day. The smaller dips show the reduced demand over weekend in comparison to working days of the week. The underlying data shows the sharp drop that has remained lower this year due to the impacts of COVID-19. Using the same time frame and units, we can show other energy vectors to get a better sense of the scale and seasonality of the existing energy system. The blocky grey line shows the demand for liquid fuels on a daily basis. The reason it is blocky is the underlying data set from the Department of Business, Energy and Industrial Strategy is available at a monthly level. Prior to COVID, the energy demand for liquid fuels, petrol, diesel and aviation fuel was between 1.5 and 1.8 terawatt hours per day. Interestingly, the demand typically shows little seasonality other than some in aviation fuel. We can see that there has been a staggering drop from the impacts of COVID-19 measures on liquid fuels. What does show in terms of seasonality is the dark blue line on this chart, which shows the total daily demand for natural gas less exports. This natural gas demand includes gas to power stations, gas delivered through the local gas network to homes and businesses, gas to industry connected directly to the transmission system, and gas to storage. Although the electrical system has significant seasonality itself, the change in the red line between summer and winter, this is much lower in absolute terms in comparison to the seasonality displayed by natural gas. The largest driver for seasonality for the demand for gas is through the local gas network, where a major fraction, particularly through the heating season, is from space heating and hot water demand. In terms of the seasonal and overnight or within-day flexibility of Britain's non-transport energy systems, natural gas currently provides the majority of this flexibility. In essence, natural gas currently underpins the flexibility of Britain's existing energy systems. However, this is neither low carbon nor sustainable. This chart is the previous chart with the y-axis now scaled to be able to show the total amount of gas in storage, i.e. the combined state of charge of the liquefied natural gas and cavern storage facilities. These provide up to 28 terawatt hours of chemical energy stored within the national boundaries of the UK. We can see the benefit of this storage called upon to provide resilience to extreme weather events such as the Beast from the East on the 1st of March 2018, where we can see a significant drop in the amount of gas stored as it was released into the gas system. Although this storage is broadly charged over the summer and discharged over the heating season, the shipment of LNG has disrupted historical patterns of summer and winter price spreads, a factor in the closure of the UK's only seasonal storage facility. The requirement to hold as little as tens of terawatt hours of energy within the UK's boundaries is made feasible by the ability to ship and import terawatt hours of energy into the country. Taking a closer look at the electrical system, we know that Britain has reduced its annual electrical demand, has shifted coal generation off the system, and has incentivised wind, solar and biomass generation to take its place. This chart displays annual data from 2009. We can clearly see the reduction of electrical demand since 2010 of nearly 50 terawatt hours. This was a significant factor underpinning the ability to reduce coal generation. This shift from coal generation in particular to natural gas, wind, solar and biomass has led to reductions in the carbon intensity of Britain's electrical supply. Continuing with annual data, but now displaying the data as percentage rather than in absolute energy terms, we can see the growth in renewable generation, particularly wind. Highlighting the percentage of generation from coal and natural gas, i.e. from fossil fuels, we can see a steady decline from 2010. In 2020, helped by the reduction in overall electrical demand from the impacts of COVID-19, fossil fuels generated a third of Britain's electrical energy. In comparison, highlighting the percentage of generation from weather-dependent renewables, from wind, solar and hydro, we can see the opposite, an increasing trend from 2010. Again, in 2020, influenced by the impacts of COVID-19 on a reduction in overall electrical demand, weather-dependent renewables generated a third of Britain's electrical energy. Finally, the remaining third of electrical generation in 2020 can be seen to be comprised of nuclear, biomass and imports. Therefore, in 2020, Britain has an electrical generation of a third from fossil fuels, a third from weather-dependent renewables, and a third from nuclear, biomass and imports. Notwithstanding the impacts of COVID-19, this is not something that many observers would have forecast with much certainty, not even 10 years ago, and is a lesson on how rapidly things can change with well-developed policies and incentives. However, using values for the full year for 2019, we can see that there are still 120 terawatt hours of fossil fuel generated electricity remaining to be replaced with a lower carbon alternative. If of interest, over 11 years worth of the half-hourly electrical data underpinning these charts and analysis has been cleaned and provided with a date-time stamp and is freely available to download from the Zenodo platform at the link shown in the slide. Using the historical data, we can see how much additional wind and solar generation is available in comparison to the previous year. Although a rather mixed picture in the early years due to several factors, we can see the average over the recent years has been broadly 10 terawatt hours per year additional generation from a combined total of wind and solar. The reduction in subsidies for solar can be clearly seen in the data for additional generation from solar in 2019 compared to 2018. Although this data is weather dependent and also impacted by curtailment, the supply chain would seem capable of scaling up its output to provide 10 terawatt hours of additional generation per annum. Of particular note with this chart is the reduction in wind generation in 2016 in comparison to 2015, as 2016 was a less windy year. This is something that energy systems of the future will clearly have to take account of and suggests that a store of tens of terawatt hours of stored energy will continue to be strategically important. This chart shows the running sum over the year for wind generation using half-hourly data. Looking at this data for 2020, the black line, it seems that wind is on track to deliver an additional 10 terawatt hours of additional generation in comparison to 2019. By August 2020, wind generation was 40 terawatt hours from an installed capacity of 24 gigawatts. This is on track to be close to 70 terawatt hours for 2020. If this was used for sustainable hydrogen production at 70% efficiency, this would equate to 49 terawatt hours of sustainable hydrogen. So, as a sense of scale, all the output of wind in Britain in 2020 could generate nearly 50 terawatt hours of sustainable hydrogen. If the UK had an additional 10 terawatt hours of electrical generation per year, within the existing energy system in 2020, ignoring supply chain limitations and taking a high-level approach to consider different avenues, if this 10 terawatt hour of additional electricity was used to displace 10 terawatt hours of electrical generation from combined cycle gas turbines, assuming the emission factor for wind is 0 and combined cycle gas turbines is nearly 400 grams of carbon dioxide per kilowatt hour, this would equate to nearly 4 million tonnes of CO2 reduction. If, however, this 10 terawatt hours of additional electricity was used to create hydrogen at a 70% efficiency, and that is taken from Germany's National Hydrogen Strategy document and may be too high when all losses are considered, assuming this has an emission factor of 180 grams of carbon dioxide per kilowatt hour thermal, this would equate to nearly 1.3 million tonnes of carbon dioxide reduction, if, that is, the natural gas was going to be combusted for space heating or hot water, for example. If, however, this 10 terawatt hours of additional electricity was used to power electrical heat pumps, to produce space heating and hot water, assuming a seasonal performance factor of 3, then the 10 terawatt-hours electrical energy could displace 30 terawatt-hours of thermal energy of natural gas. This would equate to 5.4 million tonnes of CO2 reduction. There are also potential significant CO2 reduction benefits of using the additional 10 terawatt-hours of electricity to displace petrol and diesel using electric vehicles. From a near to medium term perspective, and accepting there are hard constraints on the amount of additional electrical generation over the next decade, there are logical reasons to question why the UK should seek to develop a sustainable hydrogen supply chain from an emissions reduction perspective. Simply put, there are likely to be greater emissions benefits in the near to medium term to use any additional electricity to decarbonise in other ways than using it for sustainable hydrogen production. However, if one accepts that hydrogen will be a critical component in future energy systems, including the UK energy system, and that hydrogen from any fossil source is unsustainable, then it follows that a sustainable hydrogen supply chain of significant scale would need to be developed. This could be left to other countries to develop, but there are a range of benefits to the UK to develop an indigenous supply chain. The balancing of tens of terawatt-hours of otherwise curtailed electrical generation from over 100 gigawatt of installed renewable generation capacity likely to be deployed in the UK in future should be a significant driver in the development of a sustainable hydrogen supply chain. The challenge the UK has, similar to other countries such as Germany, is to develop a sustainable hydrogen supply chain so that it can replace fossil-based hydrogen over an appropriately rapid timeframe. Blue and turquoise hydrogen can be a transitory means to an end, with the end being sustainable hydrogen production at scale. In essence, the world will need sustainable hydrogen to be able to accelerate away from fossil fuels. This opinion is based on some assumed trends in global energy out to 2050 and beyond. These are energy systems around the world will continue to decarbonise, but the pace of this will continue to be unique to each country. Countries will continue to exploit their indigenous energy resources. Renewable resources, particularly renewable electricity, will continue to gain primary energy market share. Countries will seek to reduce energy demand and become more energy efficient as a means to limit their import dependency and maximise the use of their indigenous primary energy sources. And embedded carbon in goods and services will start to attract meaningful tariffs at import boundaries as trade areas seek to limit the risk of carbon leakage and develop comparative carbon advantages. There will continue to be energy exporting countries and energy importing countries underpinning the need for seaborne energy transit at a scale of tens of thousands of terawatt hours per year, i.e. greater than 10,000 ship journeys per year, each delivering greater than 1 terawatt hour of energy. Stored energy in a fuel will continue to be the main method of shipping energy around the world due to the comparative advantages of energy density and the power rates for loading and offloading the energy from the ship. It is difficult to see electrochemical and thermal energy storage displacing fuels as the mainstay of energy shipped between nations. Hydrogen has had levels of interest before, so what is different now? Since previous cycles of interest, international climate ambitions have markedly increased, such as the Paris Agreement. For the UK in particular, the biggest difference is the net zero greenhouse gas target by 2050 that was enacted in 2019. This means that all sectors, industry, agriculture, transport and households have to play a full part. There are limited options to decarbonise some of these areas. Hydrogen is seen as a useful energy vector and feedstock that can provide routes to do this. Also, there is a greater interest from oil and gas majors and policymakers too. The UK has a number of comparative advantages for the development of a hydrogen sector, not least a legal net zero greenhouse gas target for 2050 with broad parliamentary support. It has a number of well-defined offshore locations for carbon dioxide sequestration for blue hydrogen. It has reasonably well co-located industrial clusters with these offshore carbon dioxide locations, helpful for capturing industrial emissions into a developed CCUS infrastructure. It has a vibrant hydrogen innovation landscape, currently investigating the challenges of hydrogen infrastructure and delivery. It has a world-class academic and private sector research base, significant energy companies, energy and engineering consultancies, finance sector and legal and insurance sectors, and it has a significant offshore wind resource. These are comparative advantages that many other countries in the world would perhaps like to have the option of exploiting. Another area that the UK may wish to consider in terms of these comparative advantages is that other areas of the world have signalled their intention to develop supply chains. Regardless of the amount of innovation and deployment in the UK of hydrogen technologies and infrastructure, other areas of the world seem interested in taking advantage of these opportunities afforded by a growing hydrogen sector. Europe, Germany in particular, Japan, South Korea and China each have advantages to develop supply chains. A coordinated approach in the UK would provide the best chance of its success to position the UK as one of the best places internationally to develop and deploy sustainable hydrogen technologies. So if the UK is to develop a hydrogen supply chain, the top three recommendations would be, firstly, to develop a clear, coherent hydrogen strategy for the UK. Secondly, the coordination of hydrogen sector innovation, deployment and development across industry, government and academia. And thirdly, to support initial markets to develop for both sustainable hydrogen and fossil-based hydrogen. A hydrogen strategy is urgently needed to map a clear, coherent and coordinated pathway to an eventual supply chain delivering tens and perhaps hundreds of terawatt hours of sustainable hydrogen each year. This would deliver a sustainable feedstock for industry for commodity products, fertilizers and chemical feedstocks, and fuels for areas that are less or unsuitable for electrification. To reiterate, sustainable hydrogen must eventually displace hydrogen derived from fossil sources. A major element of this should be an industrial strategy to increase industrial opportunities both nationally and internationally for UK-based manufacturing, and to help to decarbonise existing industry and agriculture. This strategy would accommodate a twin-track approach to the development of hydrogen from fossil fuels and from sustainable sources, with a long-term aim that fossil sources are displaced by sustainable hydrogen. The second recommendation is the coordination of hydrogen sector innovation. There have been some successful pathways of innovation in the energy space over recent years in the UK, notably innovation in the offshore wind sector. Government should assess what worked and equally what did not, and consider how learning could be leveraged across into hydrogen. For coordination of basic and applied research, a National Hydrogen Research Institute could help to coordinate and propose funding areas. This has been put forward by members of the Hydrogen and Fuel Cell Research Hub for some time. Also, use the knowledge within the existing hydrogen sector and associations to focus effort on rapid innovation in key areas. The third recommendation was to support initial markets to develop for both sustainable hydrogen and fossil-based hydrogen. So let us consider the annual data for existing natural gas markets in the UK. This chart shows the annual values of different natural gas markets from 2011 to 2019. The largest in this chart is called gas non-daily metered, and is the fraction of natural gas delivered through local gas networks that is not metered on a daily basis, that is, before the rollout of smart meters. Demand from homes, smaller industry and commerce are all within this fraction, and as a reminder, it is this that drives the largest seasonal swing in energy demand in the UK across the whole energy system. Gas daily metered is also delivered through local gas networks, but is large enough to warrant a meter that provides the gas distribution network operator with at least a daily reading. Gas to industry, gas to power stations, and gas to storage injection are all self-explanatory fractions. This chart shows the values for 2019 in a different format to provide an easier sense of scale. From the earlier slide that presented the running sum of wind generation for each year, we can see that the wind generation for 2019 was nearly 60 terawatt hours of electrical energy. At an assumed efficiency of 70%, the output of all wind generation in 2019 would therefore produce 42 terawatt hours of sustainable hydrogen. Interestingly, a similar level in energy terms to the amount of natural gas for industry connected to the transmission system in 2019. Although the breakdown between feedstock and natural gas for combustion in industry was not found, this high-level comparison again provides a sense of scale. This slide disaggregates the previous 41.8 terawatt hours of total industrial demand of natural gas in 2019 into the different industrial locations, using the value of 24 gigawatts of installed wind capacity on the UK system from Renewable UK's website, and also forecasting this will output close to 70 terawatt hours of electricity in 2020, coupling this to an assumed 70% efficiency value for sustainable hydrogen production gives an approximate value of 2 terawatt hours of sustainable hydrogen for every gigawatt of installed wind. This is a mixture of current onshore, offshore, and with curtailment. The values of additional wind capacity are written below the 2019 values for natural gas demand, and this also provides a sense of scale of the capacity of wind generation needed to create the levels of sustainable hydrogen for these industrial areas. So following on from these slides to present a sense of scale, back to some ideas for initial market development. Accelerating innovation is a key consideration. Initial market development could be through shorter-lived subsidies for the production of sustainable hydrogen. Keeping this open could allow firms to decide which initial markets to target. The aim is to create a virtuous cycle of learning and product innovation and deployment through a significant scaling up of the UK market for sustainable hydrogen, not just electrolyzers, but also from bio-based routes. Importantly, consideration should be given on how to accelerate this technology development, perhaps by shorter periods of support coupled to more generous periods of support. The focus over the next 10 years is therefore to accelerate the development deployment through multiple generations of hydrogen technologies, rather than providing a longer-term income stream for different pools of capital. UK policy has experience of multiple forms of subsidy, such as renewable obligations, feed-in tariffs, and contracts for difference. All have advantages and disadvantages, so no implicit recommendation is made here, other than focusing hydrogen subsidies over shortened timeframes to encourage multiple generations of innovation rather than longer-term investment stability. Longer-term investment stability would eventually happen on the back of the accelerated cycles of innovation. Typical subsidy good practice would apply. A cap on the overall spend, only subsidies for a capped amount of kilowatt hour per annum or capacity installed. Several rounds of subsidy rather than open-ended, such as 1 or 2 per year, and any underspend rolled into following rounds, and where possible provide an element of competition and price discovery rather than a first-come, first-served or random choice of project or technology deployment. The development of a virtual hydrogen market could open up end-use areas initially better suited to incorporate sustainable hydrogen. If sustainable hydrogen obligations were placed on the most liquid markets for natural gas, potentially driven by a sustainable hydrogen obligation on shippers or suppliers, then a nascent hydrogen certificate market could develop. This would allow learning across the sector in preparation of an eventual market for hydrogen itself, both blue and sustainable, and encourage greater numbers of counterparties to take part in a developing market. For example, 1% of all the 537 terawatt hours of gas that was delivered through Britain's local gas systems in 2019 would equate to 5.4 terawatt hours. This would be a significant virtual market for sustainable hydrogen to be able to target. Using a virtual hydrogen market, it might not matter which end use the hydrogen was created for, merely that the hydrogen was created. This could allow sustainable hydrogen obligation certificates to be traded and a wider market knowledge to develop. It might also allow the market the flexibility to decide where to innovate and deploy generations of technologies and provide the scale needed to drive learning rates through the supply chain. The ultimate aim is to drive technology and installation costs down through innovation and learning rates, and for this to happen, the sector needs appropriate markets to target. As with any other energy vector or technology, hydrogen, blue or sustainable, is not a panacea for greenhouse gas reduction. Nonetheless, hydrogen is increasingly viewed as a critical component of sustainable energy systems at a global and a local level. And to be able to shift away from fossil fuels, the world is likely to need sustainable hydrogen to provide the basis for a store of energy, either itself or as part of other synthetic fuels. However, given hydrogen's utility, there is a potential risk that hydrogen is viewed as a panacea for greenhouse gas reduction. Hydrogen is not the only route to greenhouse gas reduction, and sustainable hydrogen, or fuels derived from that, all have penalties: financial, energetic, and sustainable. For every end-use case, we should therefore continue to ask, is it feasible to use the electricity directly, i.e. without the need to transform the electricity into hydrogen? This is, however, a complex question involving many trade-offs between the choice of infrastructure at a local, regional, and national level. It brings to the fore questions surrounding security of supply and the resilience of networks and their energy vectors to cope with extreme weather events. However, if we do not develop a supply chain for hydrogen in the areas that it is well suited, the question does arise as to what could be used instead. We need to develop a sustainable hydrogen supply chain precisely to substitute for fossil fuel-based hydrogen, and as experience has shown in renewable generation technologies, impressive cost reductions are possible through learning rates and innovation, but these take time. The UK has a number of challenges that hydrogen can help to solve, and it has a number of comparative advantages to the development of a hydrogen supply chain. Thank you for listening to this webinar. I would be delighted to answer any questions.
Thank you very much, Grant. That was a very clear and thought-provoking presentation. And now I'll open up to questions. Unfortunately, we've been having some technical problems with the question feed. Thank you very much, Grant. That was a very clear and I'm getting some feedback. I'll turn off my other session. We've been having problems with the question feed. We're trying to resolve it at the moment. So what I'll do is I'll start off with a question myself for Grant to answer, and then during that time I'll try and get the question feed sorted out if I can. I've actually got one question sent through by the event organizer, which I can ask you, first of all. How do you counter the argument from some in the transport sector that hydrogen from solar and wind is a poor use of the resource due to high losses from a well-to-wheels perspective?
Well, I think first thing, just to double check, because of the technology, can you hear me okay?
Yes, I can, yeah.
That's fine. So there is clearly an argument. I think it's a matter of timing. So within the presentation, we did take a very high level look at as the existence at the moment of the UK energy system. There is an argument to say that from a perspective of decarbonisation, that you are better using additional electricity, be that from solar or wind, to help to decarbonise other areas. However, there is also the argument that says there are many areas where hydrogen is better suited regardless of the losses, regardless of these particular technology issues, because there are very, very other limited options available. Now, if there were other options available, then that perhaps would be different. But one of the points is, if you're looking at certainly some of these areas of transport where electrochemical and batteries are not seen as a particularly good technology choice, then what are your options? And many of these track back to either hydrogen itself or hydrogen as a molecule that is or an element put into other things such as ammonia for shipping, or put with carbon for to make liquid hydrocarbons. So I think equally back to this point about the energy hierarchy from the IMechE is to look at, okay, well, what are your options? And hydrogen, it's not to say, as we ended this by looking at, it's not a panacea for everything. It's use hydrogen where it makes sense to do so.
Thank you, Grant. Next question is, if local gas networks were targeted for hydrogen market development, the network infrastructure would need to be upgraded to carry hydrogen without excessive leakage. Would it not be better to focus on industrial clusters and hydrogen storage for transport fuels? And there's a related question in part which refers also to leakage and whether remote fuel cells should be used to deliver electrical energy to households. So those two questions are about the balance between distributed infrastructure and local clusters and the safety issues related to those.
So in terms of looking at infrastructure, or let's say infrastructure repurposing or infrastructure development to accommodate hydrogen, then equally this thought about having a virtual hydrogen market, that would be one element as part of that, where indeed it may make a lot of practical sense to target sustainable hydrogen production to the industrial sector, and therefore to limit some of the upgrades that are required in the short to medium term in other areas. There is a lot of work going on in terms of understanding the leakage from local gas systems. It's still ongoing work. We don't know what that might be. Exactly, there is uncertainty around that. So until that uncertainty is becomes a little bit more certain, I think clearly it's an issue, but we don't necessarily know the scale of that at this point.
Thank you, Grant. I should add at this point that it was going to be in Arbon hosting for those of you who are looking forward to his contribution from the website. But unfortunately, there's been a big internet down floor in Scotland, and so he's unable to be here. The next question is, can you tell us the costs of producing hydrogen via renewable energy and electrolysis?
No,
the cost issues.
I cannot do that. So
no, but would you like to? Sure, but perhaps, Grant, you might talk about the principles when we think of the energy balance, and we've got successive losses in production of hydrogen, and it's going to affect end costs of the consumer, isn't it, compared to current energy prices? Is there something you can tell us about along those lines, what the conversion losses will do to the costs for our heat and electricity?
Well, clearly, if there's additional efficiency losses, then you're not getting back as much energy in whatever form as you're putting in. So that would, everything else being equal, increase the cost to the end product, the end user, effectively.
Mm-hmm.
But
with Ofgem, yeah, sorry.
So, please, on you go.
Well, I was just saying, I mean, with Ofgem pushing to drive down costs of the consumer, how do you see the consumer acceptance of hydrogen from a cost perspective?
Well, I think it has to be balanced with. It depends on your market that you're talking about. So, there are overall costs to the consumer. It actually depends on which market you're looking at. So if it was to replace transport fuels, for example, then government has some ability to make the taxation around that less than it perhaps would be for current fossil fuels. So there is some element on that. If you're talking about what it would do to offsetting or be a like-for-like comparison for space heating and hot water for an end user, then there is less opportunity for government to do that because of the taxation around natural gas for domestic heating and industrial heating, for example. Yeah. So if there are elements to that, that is something that really clearly needs to be considered from a perspective of if the costs are going to increase because it's hydrogen, and that is something that people will have to pay in essence to heat their homes, then we have to also align that in parallel with making sure that the amount of energy required to keep people comfortable in their homes is less, i.e. we need to have a ambitious, robust retrofit program alongside that to help manage any increase in costs from shifting to a lower carbon form of heat, if that was going to be developed.
Thank you, Grant. How do you compare hydrogen with other possibilities like ammonia for the future of the UK?
So again, I think ammonia has its place. My personal view is that the future will be very similar to now, in as much as we will very likely have a range of fuels, albeit they will be low carbon fuels. We will have a range of fuels in the future. It will not just be one, it will not just be hydrogen in essence as itself. So ammonia has its place for sure. There's a lot of interest in that in the marine sector at the moment. But there are limitations to that too. There are advantages, like all fuels at this point in time. There are a range of fuels because they serve end users with a balance between advantages and disadvantages. And I think the future will be the same, albeit the difference being that if you track back fuels in the future, synthetic fuels to make low carbon fuels, they all track back to making hydrogen at some particular point. So that is where hydrogen becomes very, very important in terms of if you want to have the ability of energy dense fuels that have the ability to shift around, perhaps to ship, perhaps to store, then hydrogen is key to doing that.
Thank you. Next question. I find it shocking how little the UK supply chain has benefited from offshore wind. If additional offshore wind capacity is required, then supply chain development and incentives or protection should not be underestimated. So we've got experience of resistance to development of key infrastructure in other energy areas, and what you've projected is quite a major undertaking potentially with hydrogen, and so how do you see? I mean that's more of a statement than question, but following on from that, how do you see as a country we address the infrastructure challenges, and including the political approach?
I think that's quite an expansive question, because it goes to, we are an open capitalist economy, and therefore how does the nation take advantage of some of the things that are going to change effectively in terms of supply chains and all the rest of it. So it is a really difficult one. It's a very political question, so I'm not going to attempt to answer that at all.
What about from an engineering perspective? Is there anything engineers can do to move this forwards?
Well, I think one of the things is that we're not starting as a nation from a standing start, from a blank sheet. There are, as pointed out, and as many other people have pointed out as well, there is an awful lot of pre-existing experience and knowledge within this country. What is desperately needed is a hydrogen strategy to provide at least a coherent sense of direction, and also, hugely importantly, is to provide markets and home markets for technologies to develop. I'm sure there are a range of different opportunities that governments, or the UK government in particular, can seek to try and encourage a domestic or an indigenous supply chain. But at the end of the day, it is an open capitalist economy, and therefore, if you could have very successful companies being grown, and then at some point other international owners, international capital comes in and buys them. So I don't know really how to attempt to answer that, because it's a situation we're in as a country.
Yeah, it's difficult. But there's a question along that vein. How close do you believe we are from producing a long-term UK hydrogen strategy, given that all incoming governments like to tinker with things and change them to their own initiatives?
I hope there's momentum to look at trying to do this on a timeline that would be, let's say, appropriate, even with COP26, which is now in November 2021. So something over the next year where a hydrogen strategy would be put forward by UK government and coalesced and brought together. So as a cross-department hydrogen strategy. There are many, many people asking for this now. It's not as if it's not unknown. So it's just a matter of a time frame. So I think many people, including myself, would hope that is, by next summer. Plenty of time before COP26, conference of parties, the UN, FCCC in Glasgow, provides an opportunity to do so.
Okay, sure. Thank you. Next question. It's a disadvantage of the UK that the net cost per megawatt hour of wind versus solar means the cost to generate hydrogen will be much lower in other countries, for example, in North Africa. Does it not make most economic sense to import hydrogen at lowest cost rather than locking UK PLC into high-cost hydrogen generated in the UK, thus embedding competitiveness into UK manufacturing? And I think I take it. I mean, with wind, we're being expensive. If we're talking about comparison wind and solar, maybe they're referring to offshore wind, because onshore wind is our cheapest form of renewable electricity and cheaper than solar power in many countries. But I suppose the principle there is that there's significant resource overseas that could be less constrained at a lower cost. And how would you see the balance between UK hydrogen industry and importing the product from overseas?
So again, it's a rather a rather wide question. I think in principle, I tend to agree with the question as to why would you, but there are other elements at play here, which is if you do have an indigenous supply, you've also got an economic multiplier within the country as well, which is perhaps not taken account of quite as much as it should be. There's also the issue of, back to the earlier question about reductions in efficiencies along the supply chain. So for sure, there are other countries and other areas of the world which will very likely have cost of electricity production and, let's just say, cost of hydrogen production at a lower cost than the UK, but it still needs to get here. So there are still efficiency losses in whatever manner, if it's changed to ammonia, if it's liquefied in terms of hydrogen, it still needs to get here. So there are a bunch of elements in terms of, it's not an easy question to answer at this particular point. But,
no, sure, there's a balance, and it depends on, I mean, the case of wind energy, worth pointing out that the onshore wind has been very constrained over the last few years and continues to be so. So that, whether that comes back or not will affect the economics, won't it?
I think for sure. So, equally, there's this issue of this flexibility, and having a sustainable hydrogen supply chain, a sustainable hydrogen infrastructure in the UK provides that ability to soak up otherwise curtailed electricity. So that in itself is an advantage to having at a whole systems level at a UK basis.
Yes. There's a question about water vapour being a more intense greenhouse gas than CO2, or be it that placed in the atmosphere at low altitude, it rains out again quite quickly. Do we understand the effects upon the atmosphere and global warming of replacing hydrocarbon fuels with hydrogen? So are there any wider impacts that need to be taken into account in the determination of its sustainability?
There may well be, but it's not something
No.
I have come across at the moment.
No. A question about the safety, and one is, I'm curious about safety. Question is, I'm curious about the safety implications of hydrogen storage, transport, and use. How safely can we undertake these processes? What is the potential for disaster?
So, a week ago there was one of the largest explosions with ammonium nitrate in Beirut. So I think we're all very conscious of the fact that any fuel has the potential to cause, when stored unsafely, when the safety regime around it is limited, that there is the potential for very, very bad things to happen. Now, we have an excellent safety record in this country. We are approaching it in a very logical manner, i.e. approaching it as in hydrogen, and whether hydrogen, or for that matter ammonia, or for that matter other things, are suitable for particular end uses. And I think the sector is very, very aware of the absolute importance of making sure that the evidence base around safety for hydrogen is as robust as it possibly can be, because they are aware that there is an element of public discourse in terms of the safety around hydrogen. I mean, from an industrial setting, hydrogen is used day in, day out through industrial settings around the world. So it is a matter, such as any fuel, is building up experience, building up the correct safety considerations, having that robust around it. And this is from an engineering standpoint. It's just that it is just another fuel, and therefore sure. We just need a different set of criteria and conditions to make that safe.
Okay, well, thank you very much, Grant. I'm going to have to bring the questions to an end now. We come to the end of the webinar slot, but I'd like to say thank you very much indeed for that very wide-ranging and insightful presentation, which has provoked some really good questions from the audience. And it's very clear there's a lot of thinking to be done, but globally on hydrogen as well as nationally, and it's something that as IMechE and ESG will be continuing to address, and I'd like to think that we'll have subsequent webinars and other forms of information on hydrogen as we work towards the best global solutions together and as engineers. So please keep an eye open for further ESG events, and we look forward to further engagement with you all. And thank you for attending. And many thanks again, Grant. And with that, I'll say goodbye to everyone.
Okay, thank you, Rupert. My pleasure.